So today our lecture is going to be on bolted connections. We are starting connections from today. So we have two types of connections. The first one is bolted connection, while the second one is welded connection. So in design of bolted connections today, we'll be going into bolted connections. And within bolted connection, we'll be having two labs. So today's lab is going to be on design of bolts subjected to direct shear and design of bolts subjected to direct tension. Okay. Now the big question is, what do we mean by direct? When I say the bolt is subjected to direct shear, or when the bolt is subject to direct tension, what do we mean by the word direct? Okay. So direct, when a tension or shear forces are acting on a connection which passes through the centroid of the connection, it is known as direct shear. Okay, so a direct shear or direct tension. For example, in this figure we have a tension member. Two tension members are connected at this joint, and we see that the forces pass through the centroid of the bolts. This is the centroid of the bolt, this X, what I've marked here, and the load acts through the centroid of these bolts, which means that the shear is direct. Okay, if the centroid is somewhere else compared to the direction of the load, we see that it's an indirect shear. So for today's lab, we'll be discussing about direct shear. For the next, now what about direct tension? When we see that the centroid of these four bolts lies over here, and when the tension acts exactly at that point, we call that it is a direct tension. It is a case of direct tension. Now, as you may have already received, as you may have already seen your lectures on bolted connections, I'll just revise the types of bolted connections. We have basically two types of bolted connection. The first type is called bearing type connection. Okay, when I say bearing type connection, it means that the bolts are tightened manually. That is, they are not fixed using machinery. They they are just bolts are tightened manually, and movement of bolts is allowed, like lateral direction. For example, you're pulling this tension member on these two sides, or you can say pulling or pushing, it doesn't matter. You see that you allow this bolt to move and bear on these surfaces. For example, you see in this figure, you see that there are two critical zones uh, that is considered while design when we are dealing with bearing type connection. The first one is the shear in the bolt. You see there is a shear plane right here, and then when you pull it on, when this thing is under tension or compression, this is a shear plane, and we need to design the bolt way. This is one of the design criteria that we use for while dealing with design. And the second part is bearing on the plates. So when you start pulling it on this side, for example, I pull this tension member to the right, and automatically there will be a reaction on the left. You see that the surface of this bolt will bear on the surface of this uh, tension member, or whatever this connected member. So this is something that we'll be discussing in detail as we go ahead today. That a bearing type of connections, there are two things that we check. One is the shear in the bolts, and the other is bearing on the plates. So there are equations given to you in the manual that we check both of them and find the capacity based on those, and then we choose the least because the lesser one would control. Now as we go ahead, we see that there are two types of, within bearing there are two designations, where this is A325N or A325X. This is A490XN and A490N. This 325 and 490 relates to the strength, while N and X means threads are excluded. For example, you see in this, you see where is the shear plane? The shear plane is over here, right here, right here. And the threads are excluded. The threads don't appear in the shear plane. Okay, so the shear plane does not cross the threads. While in this case, it is case N, which means threads not excluded, which means threads are included. I know it's a weird way of saying it. It's threads included, which means threads not excluded. So this is type N and this is type X. So in the manual, you see that the strength, the shear strength really varies for these cases. And if you take a closer look, we see that the strength of N type will be slightly less than the strength of the N type, because you see some cross section is shaved off because of these threads. Okay, so this one usually has a lesser shear strength compared to this one. Not shear strength, shear capacity compared to this one because of lesser cross section. Now, in bearing type of connection, shear strength, the shear capacity and tension capacity is calculated from the same equation, which is in the manual page. If you could just go into, I suggest you all to open your manual into page. I would say page 16.1124. 16.1, page 124. Have you opened the manual? Page 124. Page 16.1.
Yes.
124.
124.
Yes.
Okay. You see that the heading is tensile and shear strength of bolts and connected parts. This equation is used for both shear as well as tension. Okay. What changes is, if you look into the next page 125, you see that Fn, so it is based on the requirement. If you want tensile stress, we have Fnt, and if you want shear stress, we have Fnv. Now Fnt and Fnv is given to you on page 16.120. 16.1, page 120.
Yes.
Values of Fnt and Fnv is given. Okay, so it's based on the problem. So if your bolt is subjected to direct tension, we have to use Fnt, while if you're talking about direct shear, you have to check Fnv. Is that clear?
So where
Yes.
is FMV? Oh, okay.
It's given on that table. Page Fnv is given. It is table.
120.
Yeah, in page 120 in table on we have three columns. The first one is description of fasteners. We have, you see that there are two groups, group A and group B. In group A, there are two types. You see that the first one is A325N and the second one is A325X.
Oh,
Okay, if you want, you can yeah, you can note it down. The top one is, because it's not excluded, that is type N, and it is excluded is type X. So A325 type N, A325 type X, and then below that we have group B, that is A490N and A490X. The fourth one is A490X. Okay, you can see that A325X has a slightly higher FNV value compared to A325N. You can see that A325, the FNV value for A325X is 68, while the value of FNV for A325N is 54.
On the same table, right, Doctor?
Yes. For
On the same
FNB.
table.
Yeah. Okay.
Okay. So, uh, so this is uh, one of the requirement as we discussed earlier. In a bearing type of connection, uh, we have shear and tension, and then you have the next criteria, that is bearing. Okay. So for bearing, this equation is available on page 16.1 127. Page 16.1 127.
Okay, before you go there, on page 124, we have two
Yes.
equations for Rn. One including Fn, one including Fnt dash. Which one should
Yeah,
we
that's
use?
something else. We use the first one.
The first one.
Yeah, the other one is combined tension and shear. For example, in the same problem, we have tension and shear appearing together.
We will not consider it here.
Yeah, we'll do it in the next lab.
Okay.
We have that in the course we have this, but for today's we are only dealing with either direct tension or direct shear. We're not worried about direct combined cases. That is next lab. Okay. So for today's lecture, we are going to be using the first equation,
Okay.
FNAB. Okay. So the next equation is for calculating the bearing strength. Okay. So that is given to you on page 16.1 127. Okay. In that case A, you see that the case A, in a bolted connection with standard oversized short slotted holes, we have two cases where deformation at the bolt hole at service load is a design consideration, when deformation at the bolt hole at service load is not a design consideration. Okay. Usually we use the second one.
It means we have the ultimate load,
Yeah, for ultimate load case, we use
the second one.
case 2. Yeah, the second one. Okay. So this is how we calculate the strength of a bearing type connection. We have two criteria that needs to be checked. One is the shear and the other one is the
Bearing.
bearing. Okay. Now in the next slide, we have another type of connection known as slip critical connection. This type of connection is known as slip critical. Now the bolts are tightened using machines uh, such a way that uh, these surfaces get pressed on each other and there is friction developed. You understand the idea? We have, for example, we have two plates, one on top of the other. We use bolts, we use machine to tighten it to a specified tension in the bolts. Okay, and these tension would create what? Friction on these between these surfaces. And these surfaces and this friction is what that resists the loads between the two members which it connects. Okay. So in this type of connection, we do not allow the movement of bolts under the load, and the load is transferred through friction between this plate surface, and this friction is caused by the pretension in the bolts. Okay, and the designation is A325 SC means slip critical, and A490, that is group B bolts. It's an example. A490 slip critical. Now, for calculating the strength of bolt in slip critical connection, we have in uh, mm, page 16.126. Page 16.1 126. So this is straightforward because these are a few values. For example, in this case, the phi value is 1, and then you have the mu value is given to you. In mu value, the value of mu could be either zero point 0.3 or zero point 0.5. Okay, so zero point 0.3 corresponds to, it's given on the page. 0.3 mu value of 0.3 corresponds to class A surface. Okay, and class B corresponds to, class B has a value of 0.5.
0.5.
So these are two surface finish. So friction is really also dependent on the the texture of the surfaces. So class B would offer a higher friction. Okay, and then you have a term called du, capital Du, which is taken as 1.13. There's a factor, and then we have a value of hf. Okay, which we usually take as 1, and the value of tb is to be taken from uh, table 16.1 in table J 3.1, that is page 16.1119. tb is from page 16.1 119. Okay, now the last last term here is ns. N is the number of slip planes that's involved. For example, in this case, what is the value of ns? The above figure. The value of ns is 1 because there is one slip plane involved. Okay. Now in this case, where you have three plates, the value of ns is 2 because there are two slip planes involved. Okay. Is it clear? You have any question here?
Yes, clear.
This is today's lecture is going to be relatively simple because it's just small equations and then it's easy. Now the next is just to see the steps in the design of bolted connection. Okay. The first design step is to identify the weakest plane uh, in the cross section. TB. Someone asked. TB means bolt pretension. It is given on page
16.1119.
119.
Doctor, in the manual, the capacity Rn mu isn't written there.
Yeah, it is actually a misprint. Even in my manual, it is not there. But I checked some other editions, and this mu is missing in some of the manuals. So
Okay,
mu
so
is to be added.
we will add it.
Yeah, you have to add mu because this screenshot that I have shown you is taken from the AIC website. There's a screenshot from the
Okay.
website. So this is the latest one. So I think even in my print, the value of mu is missing. I mean, the mu is missing. Value mu is given below, but the term is missing in the equation.
Yes.
Okay. So the first step is to identify the weakest plane uh, based on the cross section. Okay, that's quite easy. We can identify that very quickly. And then the second step is to design the layout of bolts. Okay, the layout of bolts is based on these four uh, distances. One is the minimum edge distance, and then you have the maximum edge distance. You have minimum spacing and maximum spacing. All these are given to you on page 16.122. 16.122. So in that, all these conditions are given to you. The minimum edge distance is available from a table J 3.4 from the next page in page 123, which is dependent on the diameter of the bolt. Okay, so each diameter has a specific minimum edge distance. The maximum edge distance is taken as the minimum of 12 times the thickness of thinnest member. Suppose you have two plates, the T is the thickness of the thinner plate. Okay, so two 12 times T of 6 inch, the minimum of that. And for minimum spacing, I'll tell you what do these words mean in the next page. You see, this is the spacing. Center to center between two holes is the spacing, and edge distance is the distance between the center of a bolt hole, and the edge of the member. This is called the edge distance, and this is called the spacing. Okay. Now later on we'll see uh, we'll require to use the value of LC, which is actually edge distance minus half diameter. That is the distance from the edge of the bolt hole to the nearest edge. This is known as LC. So this is how we design the layout of bolts, and then once that is done, we calculate the capacity of the tension member. For example, in this figure, this is the tension member. It could be a tension or compression member. You need to find just a moment. Okay, give me 2 minutes.
يا ساتر شكله بيجلد ابنه. أنا ما فهمت ولا شيء ترى.
Okay, so this value, now the capacity of the tension member is based on what we already studied, the capacity of tension member. If it's a compression member, what is uh, the compression that is going to act at the connection? Or in some cases, for example, in the second problem that we'll do today, we'll see that the ultimate load is given to you. Okay, this could also be TU if it's the ultimate load. Now suppose the ultimate load is not given to you, you have to design the bolts for the capacity of the member. You'll have to go back and design, I mean calculate the capacity of the tension member. We find the value of the tension member, and then we calculate the number of bolts. While calculate the number of bolts, uh, this is how we calculate. It's the number of bolts is equal to n, number of bolts is n equals PTN over PRN. PTN is the load acting, and phi Rn is calculated based on the shear capacity of, if it's a bearing type connection, as we discussed, we have a shear capacity of the bolt and the bearing capacity of the plate. Based on those two criteria we just discussed earlier, we find the capacity of 1 volt, and based on the capacity of 1 volt we divide, among these you take the lesser one, because the lesser one will be more critical, and we divide the capacity of the member by the strength of the bolt. We get the total number of bolts required. Okay, and in this type of problem we have to also check block shear uh, before getting. We also have to check block shear. You have to make sure that the layout that you have given is sufficient to resist block shear. If block shear fails, uh, you'll have to design the layout again. You'll have to increase the spacing, for example. Now, if the type of connection that you have is slip critical, it's very easy. You find the value, the capacity of the member, find the capacity of the connection based on this equation that we discussed earlier. Just divide, you'll get the number of bolts required. And in this type of problem, you do not have to check for block shear. Okay. So now let's just discuss um, a couple of problems. Yeah, you have any question from previous slide? Anyone?
I think when solve the problem, it will be like
Yeah, it will be clearer.
easier.
Yeah, it will be much
Yeah.
clearer because it's not too difficult.
Yes.
Okay, so let's move into the design of bolted connections. So the first problem is to determine the number of number and spacing of 3/4 inch bolt, 3/4 inch uh, bolt for the following two types of connection. So the first one, so I've taken one example from each type of connection. So first one is bearing type of connection using A325N. What does N mean? N means threads not excluded, which means threads are included. Threads are not included, not excluded. Okay. So then you have slip critical connection using A325SC class A surface. Okay, the plates are made using A572 grade 65 steel. Okay, assume standard holes. You see there are two plates. You have a thick plate which is plate 6 inch over 3 over 8 inch. The thickness is 3 over 8, and then you have two plates each having 1/4 of an inch. Okay, and then this, you have been told that you should have two lines of bolts. Okay, when you're arranging it. So the first step is to uh, to design the layout of bolts. As we discussed earlier, we have four lengths to be calculated. The first one is minimum edge distance. So for this bolt, for 3 or 4 inch bolt, if you go into table J34, you see that a value of LE minimum, or the edge distance minimum, is 1 inch. Okay, and then the minimum edge distance LE max is the minimum of 12 times T and 6 inch. If you take a look at this, the minimum is to be calculated is 12 times T. Now there are two thicknesses. One is 3 over 8 and the other one is 1/4 of an inch. 3 over 8 inch is equal to, just to make it easier, it's 0.375 inch. 375 inch. While 0.4 means what? 0.25 inches. Okay, so here, as we discussed earlier that we have to use 12 times T, and this T should be the thinnest. But why did I take T as 3/8 inch? Any answer? Anyone? Any guesses? Hello?
Can you repeat the question?
Yeah.
You see, while calculating the maximum edge distance, we have to use this. It should be the minimum of 12 times T or 6 inch. Now, when we discussed earlier, I said that we have to use 12 times T. The T value should be the thinnest plate, the thickness of the
Thinnest.
thinnest plate, because yeah, thinnest one would control. But here I have taken 12 times 3/8. Why did not I take 0.25?
Maybe it's related to block shear or something.
No, but I don't know that yet because I'm just starting the problem. So I'll just make that clear. You see, this member carries the load T, while this carries only T
Half
over
of it.
2. Okay, so this is together it is half inch. Together it is half inch. You see, this 0.25 and this is also 0.25. So the reaction to the force to the left is T, which is carried by a total of 0.5 inch, half inch. While to the right hand side, you have a load T, which is carried by only 3/8 of an inch. So therefore, 3/8 is more critical. Is it clear?
Yes.
Yes. Okay. So therefore, when you calculate this, you get the minimum of this one. So that is, you have two values. So now you take a value anything between these two. For example, you can take any value between 1 and 4.5. Okay. So let's take a value of 1.5. It doesn't matter. You can take 2, 2.5, 3, 4. It doesn't matter. You can go up to 4.5. Okay. So once you have selected a value, the next step is to select to calculate the spacing. Okay, now the minimum spacing is calculated based on s is equal to 3 times the diameter, so you get 2.25. Your maximum spacing is selected based on the same equation, minimum of 12 times t and 6 inch. You get the value 3 inch. I mean, you take the value as 3 inch. Okay, so here again, here I have taken 0.25. Someone has dB is diameter of the bolt. dB is diameter of the bolt. Then now here again, if you take a look, I've taken the value t as 0.25. It is uh, because the, this length. I mean, you can choose based on these. It's the same. So I have taken a value of 3 inch. The maximum spacing is 3 inch. So I have made the layout. I have calculated the value of edge distance. I have calculated the value of spacing. Now the next is to compute the strength of plate as tension members. Okay, as plate as tension member. To calculate the capacity of tension member, if you remember, you have tensile yielding at gross section and tensile rupture at net section. Okay, since you have been told that you have two gauge lines here, you can easily find the value of an. Otherwise, finding an would be difficult. Okay, so therefore, a yes,
For the edge distance,
yes.
we just pick any
Yeah,
value.
we pick a value. Unless it is
Between
given, you can, yeah, between the values that you found, the minimum and maximum.
Between the minimum and maximum. Okay.
Yeah, but the thing is, it's always safe to take a higher value because later on you'll have to check for block shear. So if it is too low, it might fail in block shear.
Okay.
Okay. So you calculate the value for tensile yielding. The value of ETN is equal to PFYAG, where um, your uh, here you have to take the thinner plate. It is 3 over 8. So 6 times 3 over 8 will give you AG, and your AN is to be calculated after subtracting the holes, bolt holes. So, and in this case, the value of U is equal to 1. Shear lag factor is equal to 1 because you're using a plate. If you remember, AE is actually U times AN. Here, the value of U is 1 because it's a plate. So, you calculate the value as per tensile yielding and as per tensile rupture, and the minimum of these two is the capacity of the member. Okay, this is something that you know from uh, earlier lectures. The number of bolts, to determine the number of bolts, the first part of the question says that it is a bearing type of connection with A325 N type connection. So here we see how we calculate the capacity in shear. PRN is equal to PFNB. It's PFNAB, but here it is PFNB. Okay, because it is shear. So P value is 0.75. Fn equals Fnb is equal to 54 kips. Now this is available to you. You could open page uh, 16.1 16.1 page 120. You can find the value of Fnb. Okay, it is 54 for A325N. Okay, and AB is calculated as the number of uh, the area of shear planes. Actually, it's double shear. When I say double shear, what do we mean? If you have a bolt right here, if we have a bolt right over here, it is subjected to two planes of shear.
Yes.
Okay, so here when we calculate the area of when you calculate AB, we have pi by 4 times the diameter of the bolt square times 2, because the same bolt gives two planes of shear, two shear planes. So we get the double capacity from the same. In fact, it's something like that. You get double capacity from the same bolt because you are using two different shear planes. Therefore, you have to multiply it with 2. If your problem had only just two plates and a bolt in them, this value would be 1. But in this problem, we have three plates. There is one. The middle plate is being pulled on one side, while the other two plates are being pulled to the other side. The same bolt is subjected to two planes of shear. So that's why we have two. If just two plates, we would only take the value of AB as this part without 2, it's just 1. And when you plug in all these values, you get the value of PRN as 35.802 kip per bolt. Okay, this is the capacity of one, and this capacity is calculated based on the shear capacity. Now let's find the capacity based on bearing capacity. Now there is in the previous part there is a table in page 722 where you can find the value of one bolt directly. There is a table. You pick group A, and then this is type N, and then just double shear, and for this value of diameter of the bolt you can get this directly. Okay, or else we can do it manually from here. To calculate the bearing capacity, as we discussed, we have this equation in page 127, and we check it for ultimate load. So this equation can be converted into this one because there are many terms in common. It can be converted into this to reduce your effort in calculation. The phi value is 0.75, 1.5. T is the least thickness, 3 over 8. Your F ultimate is 80 ksi for this grade of steel, and minimum of LC and 2 times diameter of the bolt. As we discussed earlier, LC is edge distance minus half diameter. Okay, this LC we already found in the beginning, so it's 1.5 minus half the diameter of the bolt. We are using 3/4 inch bolt. Half of that is 3 over 8, and 2 times diameter of the, and you have to check it against 2 times diameter of the bolt, which is 1.5 inch. And the capacity is then calculated as 37.97, and we see that from these two values that shear strength, shear capacity of the bolt is what that controls among these two. So they take the value PRN as 35.8. We substitute it here. We find the number of bolts by the capacity of the tension member divided by the capacity of one bolt. So we require 2.7 bolts. Now, once we have done this, we have to check. We have found the number of bolts, and we have been told to use 2 layers of bolt and a grid arrangement. So uh, we have to take it to the next multiple of 2. Therefore, we require 4 bolts. So this is how the arrangement looks like after we have uh, given the sufficient spacing as well as edge distances. And in calculating the block shear, we have 2 possibilities here. One is failure along in this part, where this part would stay there and the remaining would shear off. Or you could have another case in which this part would stay and the rest would shear off. So this is something that we have already discussed from in the initial lectures in design of in capacitive tension members. So we see that according to possibility 1, capacity in block shear is 132, which is higher than I think 95, the capacity of the tension member. So it is safe in this case. And in possibility 2, we get a value of 114, which is again greater than the capacity of the bolt. Therefore, it is safe once again, which means your design of bolt is done. Okay. Now this problem consisted of a member subjected to direct shear. Now we have another problem. I'm sorry, it's not done here. We have the same problem again. We have a slip critical connection. And first, we already discussed about bearing type. In bearing type, we checked for 3 things actually. We checked for, we calculated the capacity based on shear strength and bearing to get the number of bolts. Once we have found the number of bolts and the layout, we also check for the block shear. Once it is safe in block shear, it means that it is done there. Now in the same question, we have also been asked to design the connection if we were using slip critical type of connection. Okay, for slip critical type of connection, you have phi r is equal to phi mu du hf Tb and s. For phi, this is all available in the manual. P value is 1, mu value is 0.3, as discussed, as because we have been told to take class A. If we've been told to take class B, the value of mu would have been 0.4. Then we have du is equal to 1.13, hf is 1, Tb is to be taken from the manual. If you're going to page 16.119, 16.1 page 119, minimum bolt pretension is given to you. You have to find the value for A325 SC over there. I mean A325 type of bolt, and the diameter of the bolt is given, so you have to find it from there. And the number of shear slip planes is 2. So value of PRN can be calculated by just plugging in all these values. You get the value of uh, one bolt, and then now you calculate the number of bolts based on PN divided by PRN. So you get 5. So we'll take it as 6. We require 6 number of bolts if we are using a slip critical type of connection. Okay, this is how it is different. Then in this type of connection, as we discussed earlier, we do not have to check for block shear. This is it. Slip critical, designing a slip critical connection is quite easy. Okay. Next we have uh, a bolted connection subjected to direct tension. Okay, you remember is that subject to direct tension, and determine the number of 3 or 4 inch diameter A490 bolt for the connection shown in the figure. Assume the load is 10% dead load and 90% live load. Use AACLRFB. Now this question has been taken from your textbook. The same question is available in the textbook. I've just rewritten this one. The first step is to determine the layout of the bolts. Now this is the repetition of the earlier step. You see it's the same. You get okay. There is this part is actually not required because the uh, the thickness of these members are not given to you. So I think this is something that is not required for this problem because thickness of these members are not given. So in your notes I'll be removing them. What you have to calculate is TU. TU is calculated from TU is equal to 1.2 times dead load plus 1.6 times live load. All these values are given to you. Your load and tension is given to you. Calculate the ultimate load, and then PRN is calculated from PRN is equal to PFNTAB. Your P is equal to 0.75. FNT is from the table. If you go through the table, you find that value of FNT is 113 K kips, and then value of AB is 5 by 4 times the diameter square, and the capacity of one bolt is calculated as 37.4 kip per bolt, and the number of bolts can be calculated as N is equal to T ultimate over PRN as 5.82. You can take it as 6 bolts, and that is the answer. So this is done. Do you have any questions?